My name is Brian Mitchell, joined by Sherry Barr and Josiah Martin. And we're here to talk to you about our senior design, our refrigeration tutorial board. Three of our members could not attend today. Josiah Sawyer, Michael Farley, and Bryce Steyer. They're at Wind Ensemble and Spring Dance, so they had excused absences. But a little bit about our refrigeration cycles before we go really into how we design and build our board. I just want to talk a little bit about a refrigeration cycle and what it actually does. And in concept, the refrigeration cycle is actually pretty simple. You have four main components. You have a compressor, a condenser, an expansion valve, and an evaporator. And you have refrigerant running through this entire system. And so basically, the compressor will move the refrigerant through the entire system, and the condenser and the evaporator essentially move heat throughout the system. So an evaporator will take heat out of the system, and the condenser will push heat into like a heat sink. For example, in a refrigerator, the cold refrigerated space in an evaporator is kind of like the inside of the refrigerator, and then the refrigerant will go through the cycle. It will pick up heat from inside the refrigerator, and it will displace it outside of the refrigerator. And it'll keep the inside of your refrigerator cool while displacing the hot air outside. Over on the right is a TS diagram, which thermodynamic students will know about this, and I can understand some of you might not. But basically, through the cycle, the refrigerant will go from a low pressure and low temperature up to a high pressure, high temperature, before moving down through the condenser, being throttled through the expansion valve, and then moving through the evaporator and picking up at state one. And so these are the equations. These are the points that we want students to be able to find whenever they're actually running a refrigeration lab. A couple refrigeration boards we've had in the past. This is actually the third iteration. We had one built in the 1990s, and it used R22. And it was a board that did work, and it worked well. However, it did not have any electronic components. It was all gauges and all physical, so there was no electronics with it. So in 2008, they wanted to revamp the project and actually add electronics so that you could display all the temperatures, all the pressures, all the mass flow rates onto a computer. Unfortunately, when they were completed with their project, they kind of ran out of time at the end. They had leaks in their system and they were unable to present a completed project. And the board has been sitting up in the third floor of Floyd for the past 10 years. So until then, it's just been sitting there. But this year, we were able to redo the project and see if we can make it work. So our objectives, we kind of determined that the group in 2008, their refrigeration cycle should have worked, but they kind of ran out of time at the end with the actual manufacturing of the board. So we knew if we could actually complete that, we would be able to have a good board. So we wanted to demonstrate a vapor compression refrigeration cycle, which is the cycle I just talked about. We wanted to give this board with a completed lab to the thermal fluids lab, which is a lab that juniors take. And we want to include a user manual and a student lab, user manual for the professors to actually be able to troubleshoot the system, as well as a student lab for students to run through the system. And we wanted to complete that all through the board whenever we were able to give this to the junior lab. And so now Price is going to talk a little bit more about, you want to move on to the next slide? Yeah. He's going to talk about the design of the board.
Just a bit of a video for all three of these guys.
Last semester, using our basic knowledge of the refrigeration cycle, we developed a schematic of our refrigeration cycle. Now we wanted to do this so we can figure out where on the cycle we would want to find pressure and temperature. So ideally, with the four major components of the refrigeration cycle, we would want to have 8 locations, one before and one after each of the components. But unfortunately, due to budget and resource constraints, we were only able to have enough sensors for 6 locations. So this can be seen in the top half of the schematic here. For the majority of these components, there is a sensor and pressure sensor before and after each component. Now on the lower half here, you see there's 2 tanks of water. Now for most of the cycles of this size, they typically use air to cool off or accept heat from the refrigerant as the cycle is running. But for ours, we decided to use water due to the lab room having large differences in temperature and typically humidity here in Pennsylvania, that it could lead to inconsistent lab results. So with water, it's usually a room temp and it's very consistent, doesn't alter due to atmospheric pressure. Now from there's 2 pumps that pump water through each the evaporator and the condenser. Now and also on the refrigerant line, as well as both condenser and evaporator, there is flow meters to observe the flow rate of both fluids, because we're going to need this for analysis later. Now, once we were done with the schematic, we were then able to continue on to designing a detailed markup of the model of the lab. The image on the left there is our first detailed design that we had done last semester. So we were able to model most of the components. Unfortunately, some of them we weren't able to receive until after Christmas, so we went off basic dimensions. We were able to glean off the manufacturer's pages. So from there, we were able to place all the components where we thought we could fit them onto our board. The image on the right here is our final detailed design that we used to manufacture our lab. Now, major changes here is that we were able to add copper tubing elbows and T's that we're going to need to assemble for soldering, as well as we switched the heat exchangers around, so the one with more coils that would have a higher exchange rate would be on the evaporator side, as well as we adjusted the spacing because some of the components came out larger than we had previously thought. Now, a lot of this, the model we were able to glean dimensions that we were able to use to manufacture the copper tubing that we would need to solder together and finalize the design.
Now just on to Josiah Sawyer for fabrication.
So we had general fabrication was the biggest thing that we had to do this semester. We had to actually build the board, which was quite an ordeal. One of the major points of this with our general takeaways was flexibility and differing levels of experience. Now, not all the group members have had the same experience. Some have had parents with a garage full of power tools and done a lot of work in there and built up a good knowledge of how to make things, whereas others have not had so much of that. So we had to balance out who was doing which work, who would train other people, which work was easier, and how all of that was going to work out. So one of the things that had to happen was occasionally when one of the more experienced persons was in the shop working on something, they would have to stop what they're doing and go help someone who has less experience to ensure that that person is working as efficiently as possible, which increases the overall group's efficiency. Similarly, regarding flexibility, we had problems with making sure that we ordered the correct size tubing for the copper piping that we had with the refrigerant, and that caused a little problem, so we were delayed for about a week of soldering, but that ended up not being such a big issue because we had a lot of other fabrication to do, and that helped us focus on that early fabrication and get that done. Another thing we had to deal with was some setbacks, particularly this broken flow meter that really kind of freaked us out because we didn't have much time at the moment. Fortunately, we really got together really quickly. We didn't blame anyone. We just jumped on, contacted the company, seeing what we can do to fix it. We were able to replace the broken one with a faceplate from one of the water flow meters, and that worked quite well. And then when we got the new one, we just put that on the water flow meter, and everything worked out nicely. Another thing we had to deal with were getting custom parts and building them ourselves for fixing certain things on the board. You can see the blue one over there shaped like a hook. That's for the filter dryer, and then we have this other bent plate for the flow meter. So now we also have sensor ports that were a specific piece of interest for the fabrication. These were used to mount the electronic components to the board, specifically the sensors that are analyzing the refrigerant cycle. There were two styles we used, one with 3 ports, one with 2. The 2-port design was used to have a thermocouple and a pressure sensor. Then the 3-port design had a thermocouple, pressure sensor, and a pressure control system, which was used to analyze the compressor in conjunction with that. One of the challenges we faced was making it lightweight enough so we could solder it directly onto all of our tubing for the whole line without having to make an extra mount, because that would have taken a lot of extra time to do that. We also had to finish making all of these before we could do the refrigerant line, because these were very important for the whole process there. Along with just fabrication in general of these parts, we had to relearn how to use the mill, because Josiah Martin and I were the ones working on these, and we had not used a mill since sophomore lab. So refreshing on that was a little bit of a thing to deal with. And then also tapping pipe threads is not easy. It's not like normal tapping because they're conical, so you have to work a lot harder to take out all that extra material. And if you actually go too deep, it will not seal. We had a little scare with that, but fortunately everything sealed correctly. Now on the refrigeration line as a whole. So there was a lot of other challenges with this. We knew that the last team that did this, they had a lot of leakage problems. So we decided we were going to do as many solder joints as possible because those would be the easiest to do in a manner that won't allow them to leak. Even if they don't look very good, they would work well enough to keep it from leaking. The thing is that did involve us learning a new skill where a couple of us learned it, but because I started being the one doing it the most in the beginning, we decided just to stick with one person doing it so that person could gain the most experience, we'd have the best solder joints. Another thing we had to deal with was the sensor ports again. They were very large, so you had to heat them up for a long time with the torch before you actually ready to solder. That meant that we had to solder them individually and then start with those being the first piece we solder everything off that, and then put it on the board to do as little heat work around the board so we wouldn't make it catch fire or anything. We also had to figure out how we're going to space out all of our components. This involved figuring out where the air stack was going to be, which we ended up leaving to be that over there that you can see in the far right picture, that diagonal piece right by the heat exchanger. The area could allow for us to constrain 2 degrees of freedom and helped us take up all of the error at the very end. So we went with our general design beforehand, and right there is where we really adapted everything to work out.
So as the refrigeration line was going up, so was the water line. The water line can be thought of as 2 separate entities, both starting with a pump in a tank at the bottom of the refrigerator board. The pump takes the water up to a water ball valve so that the student can alter the mass flow rate of the water through the heat exchanger should they decide to do that as part of their lab. And then the water goes through the heat exchanger, comes out, runs through a flow meter, which directs the water right back into the tank. The order of installation here started with the mounting of the 2 heat exchangers, the condenser and the evaporator, so that the solder team could get going with the copper pipe. And then they also soldered on these solder to NPT elbows as well. The other type of connection we used on the water line is a barb fitting with a worm gear to an NPT with Teflon tape. The tubing was hooked up so that the heat exchangers, both of them, would be counterflow to maximize the heat transfer between the Freon and the water. And so once we finished the heat exchangers, then was the flow meters. They were mounted to the board as well as the acrylic tanks. Each of them have modified lids so that the tubes could run through the tanks and not have to take the lids off, as well as a thermocouple in each tank to get the final temperature. There's also a thermocouple right at the output of each heat exchanger. All those thermocouples run up to an electronic system there to get that into the deck. And then once we got the refrigeration and the water system up, it was time to leak test our system to see if it was leak proof. So we hooked it up to a nitrogen tank, and on the evening of April 10th, we filled it up with nitrogen, and then we came back the next day to see if it could hold a pressure and that there weren't any leaks. At first we were surprised to see that the pressure actually increased, but then we deduced that because of a higher temperature, since it was a nitrogen-oxygen mixture in the pipes, that the oxygen was just expanding, and so there wasn't any leaks. So then it was time to install the Freon. So we got in contact with Sean Barnes, Grove City College's Director of Maintenance, and he sent one of his guys over with a couple pounds of Freon to help us install the refrigerant. What he did is first he used a vacuum pump to empty the system, and then installing the R134A tank to the same charging valve on the compressor that the nitrogen tank was hooked up to. He put about 1 pound of refrigerant in, and then started up the compressor and continued to add in Freon until we saw about 100 psi pressure difference between the high side and the low side on the pressure gauges. So we were using that as our gauge to know when enough refrigerant was in there. At the same time, we were also adjusting the thermal expansion valve because we wanted to make sure that the refrigerant, when it was entering the compressor, that it was going to be a saturated vapor. And now we will hear from Michael Farley to talk about the electronics in the system.
So one of the main objectives we had for being able to create this board was having it communicate with the computer. Similar to the 2008 group, we were going to try and use electronic components to read values at specific places, particularly after each of the important components. So we looked at some of the components that they left us for the old board, which they left us a lot, saved us a lot of money. First thing would be the NI9211, which is a thermocouple reader. We have 3 of these, which enabled us to use it up to 12 inputs for thermocouples. We ended up only using 10. The next component would be an NI9205, which is a voltage reader. It reads voltages mainly for our purposes from the pressure sensors and the flow meters through a series of circuits powered by a power supply. The next component would be the DAC chassis, which is a really important component into our design. It allows us to use these prior components to read values. It's the component that talks directly to the laptop, which is a designated computer for this lab, through a USB port. They also left us flow meters, 3 of them, 1 that we were using for the refrigerant line and 2 for the water lines. They left us a series of pressure sensors and thermocouples, which we added a couple of our own thermocouples we made. So once we took inventory, figured out what we had available to us, we started testing some of these components to figure out what we could actually use in our design. We used an external power supply shown here with a few different multimeters based on what output the sensors were going to give. And we plugged these into a breadboard to create some of the circuits for the pressure sensors and flow meters. Hooked all that up to the DAC unit, which talked to the computer, and we realized that many of the pressure sensors that we were looking at were inaccurate, whether they weren't even giving us a voltage at all, or they were just giving us the same voltage whether or not we had the power supply turned on or not. So we realized that we would have to replace these, and we replaced them with 6 new Omega sensors, which are the same kind of pressure sensors the 2008 group used, except that it puts out a voltage instead of a current. 3 of these we paid for, and 3 of these were actually paid for by the mechanical engineering department. Part of the problem with trying to figure out how each of these components worked was with figuring out how they are wired. There wasn't a lot of information on this, whether it wasn't in the documentation from the 2008 group or really from the manuals for each of the components. So after some trial and error, we realized that we would need an external power source of about 24 volts for each of these, which has an input current and an output ground for each pressure sensor. And then the pressure sensor reads directly into the DAC unit and then grounds out. The flow meter is a similar schematic, except that because we're using the old flow meters from the 2008 group, we had to add in a resistor of about 280 ohms, so we get voltage from it. In order to power these, we couldn't just use an external power supply like the one we were using for testing. So we had to buy a new one, a Rhino power supply, that gives us the 24 volts we need, as well as about 15 amps of current to power all the components we need. This works in correction with the DAC unit, and we attach it to the board using a DIN rail mount and a series of signal and ground modules plugged directly into a power strip underneath the table. So working towards this objective of having it talk to a computer, we had to have the computer be able to read some of the things that the DAC was saying. So throughout this year, I've been creating kind of a virtual instrument that reads these values and displays them in real time. The part of the block diagram on the right that you can see here isn't the part that's actually reading values. There's a series of other modules in the same code in LabVIEW that reads each of the parts from the DAC unit through a driver called DAC-MX, which only works with an older version of LabVIEW, which I didn't figure out until about halfway through last semester. The part that is shown here is the arrays that each of the inputs from the DAC is sent to, and then some of the constants that they're sent through to calibrate these values and actually show you the PSI and the gallons per minute instead of just 1 to 5 voltage. The front panel here is what you would be interacting with if you were a junior student in the lab that we're trying to have this board be used in. Each of these numeric indicators is a different value from, they'll be labeled on the board. And each of the thermocouples and the pressure sensors and each of their modules are labeled. In the future, we would like to maybe have a different kind of front panel that only shows certain values so that the student just know everything as soon as they look at the board. There would actually have to be some deduction as to some work done for the lab in order to learn something about the refrigeration cycle. So this is what our final product looks like from the electronic standpoint. It is a bit messy, as I'm sure you can tell, but we would like to, in the future, clean it up, maybe reconnect some things and add some zip ties so that we, if you looked at it, you would know what was going on. Only one of our thermocouples may have malfunctioned, but the other 9 were fully functional, and we are still testing the other one to make sure it didn't work. All of the pressure sensors and flow meters do show values, and although some need to be relabeled due to inaccurate readings, we have gotten them all up to speed, and they are now giving us enough information to use in analysis.
So just one more video, guys.
Last semester, we ran a quick analysis of what we predicted the values of the system would be running at. So this can be seen in the left image on this TS diagram. Now, each of these points here, marked 1, 2, 3, 4, are points before and after each of the major components. So between 1 and 2, that's the compressor. 2 to 3, that is the condenser. 3 to 4, expansion valve, and 4 to 1 is the evaporator. Now, as Brian had mentioned earlier, this matches pretty closely to what our books had shown us what an ideal cycle would look like, which is fairly good. That means we're doing the calculations correctly. The image on the left here is a TS diagram that we made using the data that we collected when we were running our lab last week. Now, the upper portion of the TS diagram matches fairly close to the ideal cycle. You can see from 1 to 2, it does shift over a little bit more to the right, and you can see 3 kind of dips a little bit lower off the liquid vapor line. Now, that's actually pretty good because it's not an ideal cycle, so those are the kind of losses you'll be seeing the shifts in the line segments due to losses within the system and inefficiencies of heat exchangers and compressors. Now, what is not very similar is the 4 to 5 section. 5 really should be on the liquid vapor line here in the lower portion of the graph. Now, we think we determined this to be because of too large of a pressure drop from the expansion valve before the evaporator. So if we were able to raise that pressure up a little bit, it would place position 5's mixture of the refrigerant closer to what we were expecting within the system. Now, it works great. It's good the way it is, but it can come out better.
So to continue with what Price was talking about, what he mentioned there was a test that we ran through was just a simple running through of the system for about 20 minutes and gathering loads of data, the data that we could about the system. And our analysis included the ease graphs that you just saw there, which is just a program that works through, and people who are familiar with thermodynamics, or remember taking thermodynamics would be familiar with ease. That allowed us to get a quick look at how our system is comparing to the ideal cycle, like Price said. But just to continue with that, on the left, you can see what the ideal cycle equations would be between between each of the 4 states. So from 1 to 2, there is an isotropic compression, and that is the power input through the compressor. From 2 to 3, that is the heat rejection into the heat sink. From 3 to 4, the expansion valve throttling, we would say that is isenthalpic for ideal cycle. For an actual, that is approximate. For all these values, it's an approximate with an actual, and we'll do a look further into that. And from 4 to 1 is the heat absorption, or the heat that we take out of the control volume to cool. Now, on the right is essentially how how we calculate how good our cycle is running in comparison to our ideal. So for efficiency and performance, efficiency of the compressor is just looking at what it would be like if across states 1 and 2 on either side of the compressor if it were isentropic. And for coefficients of performance for refrigerant, that's just a simple ratio between the heat absorption from the control volume and our work input. So say if we were to have a coefficient of performance of 5, that essentially means that we are absorbing 5 units of thermal energy for every 1 unit of electrical energy that we're putting into the system. And the coefficient of performance for a heat pump is essentially looking at it in the stance of we reverse the entire cycle. So the difference between a refrigerator and a heat pump is just a matter of direction of flow. So if we were to reverse the direction, all of a sudden we have a control volume of what we'd be heating, and we are evacuating cool air to the other direction. So just on to the next one. These are our test results from the analysis that we ran. Some of the values from the equations just shown before. So the first 3 values are what we were expecting from our analysis beforehand. Pretty decent for power input, 243 BTUs per hour. That's slightly off from what we had from the specs for our compressor, but this compressor is 10 years old, and so we expected some change there. And then for the heat loads, heat and cooling loads, those are about appropriate for the size that we had. We don't have much to go off of, so we were happy with the outcome there. But the really interesting part, I think, is with the efficiency of the compressor. For most commercial compressors of the size that we have, which is a third of a horsepower, the efficiency is anywhere between 0.4 and 0.7. So we're kind of in the middle range there. And the coefficient of performance for the refrigerant side is actually very good. From the initial installation of the refrigerant, we actually had our control volume filling up with ice within the first 15 minutes. So that surprised us quite a bit because the system was just running very well. A little too well actually for the time space, but we were able to make adjustments so that it wasn't freezing and it wasn't hurting our pumps. But so yeah, for the commercial AC units, is anywhere from 2 to 4 for a coefficient of performance. So we're actually on the high side for that, and like I said before, the coefficient for heat pump is just more than that. Now, as a general results for the deliverables that we wanted to have, looking back at the PDS that we had at the beginning of the year, our goal was to have a working system for lab, and that's what we got. We also wanted to get into a lab report, so we are in the process of writing the actual lab report for the junior students to run through. We already ran through our own version of it and have done an ease analysis. I think one of the best outcomes for this whole system is the opportunity that it holds for design your own lab for juniors, because there's still a lot of variables that can still be analyzed. Given the time constraints at the end of the semester, we would have liked to have done more. We weren't able to completely, but design your own lab is definitely an option for the system. As well, looking back at our PDS again is the maintenance manual, and that is fully completed with any of the intricacies that, and it's just suggestions that we have for the system as we've been running it. That way, the faculty or staff who may be servicing this in years to come have an idea of what to start with. It has all the documentation and system specs, as well as safety requirements. Now, just to summarize a bit on our budget for the whole year. This is a sensitivity chart of the percentage cost for all of our categories of expenses. Now, about 70% is through components and materials, as you can see there. The components just include parts that we had to research on, purchase. 70% of our total purchasing was actually done fall semester. But some of the stuff that was done this spring included some trips to Lowe's and Ace Hardware for all the fabrication tools and things that we needed. And I think the biggest expense that we had for this semester were the pressure sensors that we had to purchase. And some of them were actually, three of them were purchased by Dr. Fair's portion of the junior labs, so thank you, Dr. Fair. And then just going along the lines, some of the minor things were just the water line fabrication components, the refrigerant line, all copper, electrical system, some wires that we had to do for purchase, and T-type thermocouples, as well as some tools for the refrigeration line fabrication. And just one last look at the budget for the Pareto cost. This is our Pareto chart. This is full dollar amount cost, and a look at the percentages that you saw earlier, but just having them add on to the full 100% budget that we had. So a budget of $3,000 at the beginning of the year. We spent about $2,450. So we're under budget with the help of junior labs, and percentage total close to our full budget.
So like Josiah was saying, we are happy with the board that we're able to present for the junior labs, but we still feel that there are some adjustments and some tinkering that we have to perform with the lab, so it's running at its full performance. The main thing that we should probably fix is the refrigerant amount. And so what we wanted is, on the expansion valve, we wanted about like 100 PSI drop, and we only got about 85. And so this might have been due to a couple different reasons. The refrigerant amount and the expansion valve might not be optimized for the full 100 PSI performance, as well as the condenser, which is right after the compressor. It might not actually be turning all the vapor into liquid refrigerant before it goes into the expansion valve, which is another thing that should not happen in the system. When Sean Bournes installed the refrigerant, he had a handheld portable temperature and pressure sensor. We were able to put this at different parts in the system, so we could easily read the difference in temperature and pressure. And so we feel like with one of those, that would really help the system, because we could instantly get the temperature and pressure just from actually plugging them into the system. The sight glasses, this is a minor problem that, I wouldn't even say a problem, but something that might need to be adjusted, is all the sight glasses are currently facing out, which is good to actually look in, but it also can lead to a buildup of liquid refrigerant. So we feel like they should be turned so they're actually facing upward, or they should be turned so they're mounted vertically. So when the system is shut off, all the refrigerant can drain out, and so there's no buildup. We also feel like, this is what Josiah was mentioning earlier, we should go for a larger control volume, because the first time we ran this, within 15 minutes, the water started to develop into like an icy slurry. And so we would like a larger volume so we can actually run the system longer without any problems, any ice building up into the pump. But with that, I think that's going to bring us to the end of our presentation. If any of you have any questions, we'll answer them to the best of our ability.
We have time for one question.
Answer one question.
What's the reverse Carnot cycle efficiency? Like, what do you expect for the efficiency, and what's the efficiency of the actual cycle? Refrigeration.
Now I don't have the number off the top of my head. We didn't. We ran that calculation for Carnot, but because of we later found we didn't present on that just because we're not confident in that value. Because the temperature sensors, the T-type temperature sensors that we have in the two tanks, those were giving inaccurate readings as of yesterday. So we don't know what happened. So we don't have the current efficiency because we can't get the temperatures.
Thank you, team.